square it,
Hi.
then you just multiply the log by 2.
Hey, we're just doing some
Okay,
math
you're
here.
on the air. You're
I
on.
know, we're doing math. I'm Ronnie Heron. Welcome to the SBAU Astro Hour. It's our view, the gentleman on the screen, of the ever-expanding cosmos for the Santa Barbara, California Telescope and Astrophysics Club, Santa Barbara Astronomical Unit. We try to cover it all, and I think we do every week on screen through Zoom. This will be program number 219 into our fifth year of telecasting every Monday morning. It'll be for the week of May 12th through the 18th. Programs on YouTube. We're based at the Museum of Natural History, and you can check out all the past programs, plus everything you want to know about our club on sbau.org. This week, we're going to cover the Cosmos 482, which finally came back home after more than half a century. A Soviet Venera spacecraft. I think it came down. You're going to learn where. Hercules and its four-star asterism Keystone. Our big full flower moon was washing out the night sky Saturday night, but we found plenty to look at anyway at the star party. A couple of asteroids involved in a game in space, drawing attention. 9 Metis versus 3 Juno. I thought sure Juno had it, but Metis came through in the end and came from behind, won 9-3. M5 is in Sirius, and that's not like somebody's
Serpents.
astrological sign in a house out there on the zodiac. We cross-section a neutron star this week, and our sun going to be entering, I guess, an era of stronger sunspot activity for 11 years. In light of a recent lady professor's throwing light on ultra-faint dwarfs, we're going to dissect galaxies. Talk about galaxies a lot. Let's meet the gang. Our beloved president after many, many years, Jerry Wilson. Pat Porges, his wife. Jerry, how are you?
Good.
We're
Good
all
morning, and hi, Joyce.
we're all going to be there at noon, no, at 1 o'clock on Wednesday for your speech to the homeowners association. At least I am. We'll see who shows. I also intended to be at county supervisors weeks ago, and it totally slipped my mind when they were talking about night sky. Here's our outreach guy, Chuck McPartland, who's nothing but awesome and a supporter of Ukraine, as we all are. As long as you have that blue and yellow sign behind you, that flag, there's still a war going on. Hope it ever goes away and works out well. Hey, Bruce Murdoch joined us. He's married to Bonnie, and Bruce is president of the Theater Organ Society. Chuck is married to a Pat, and so is Jerry. And here is Tim Crawford, who's married to Karen. Tim joined a few years ago before I did. He's an expert on stuff and catching up with the rest of us, like myself. And doggone it, if not online, is Tom Whittemore, who edits our
Morning.
newsletter. How are you, Tom? I
Morning.
always we all smell rising dough and sourdough bread when you sign on for some reason.
That's because of the distillery next door to him.
Okay, well, I'm waiting for my Christmas gift early because I remember going through that last sourdough you gave me years ago. President Jerry posts cartoons, and he has for over 4 years, and I don't know how he keeps coming up with these thought provokers, but we've got a belly full of them this week, at least 5 or 6. We'll call up on screen, and here's the one I don't remember. A couple
You're
of
about four of them that you won't remember.
All right, let's go through this together. Stick figures looking at a star on the ground, and she says to him, "Dear Oracle, what is the nature of dark matter?" And the Oracle, that's what that is, says, "Well, it's about 20 pounds." "What?" she says. And it answers, "Dark matter is a particle. It weighs about 20 pounds. It only interacts through gravity." He says, "Only gravity, huh? So none of our experiments are really going to tell us anything more about it then?" And it says back, "Afraid not." He says, "So what do we do?" Oracle replies, "You should go out for burritos." She says, "How will that help?" Well, it answers, "Burritos are pretty good on Taco Tuesday, which will be tomorrow, I guess."
Uh-huh.
Is that a black hole, that Oracle, or never mind? Here's another new one. Boy, you're surprising us. It's a
Now
little
these
washed.
came, I had to dig these out. They were very hard to get.
I could barely read it. Meanwhile, at the art college,
At AI
AI.
Art College.
oh, the AI art college. Okay. Oh, I see. Yeah. All
The
right.
artists,
There's
the
Okay.
artists are
robots.
all robots.
Now I get it.
Robots. I got to tell you. A couple of guys talking and it's washed out. Can anybody read what he's saying? Looking at the screen?
If AI is good at program, it went away.
Wait a second. Let's see, which one is that?
You always have to increase the contrast.
I have to go to a different application to show it.
Oh,
Well, why don't you show the ones we got?
Well, I want to do it right.
I have all my comments written down. Here we go. One guy says to the other after looking at the screen, the AI is good at programming, but now it's created a keyboard shortcut that requires 11 fingers. Okay,
I
I
think
don't
that's a
blame it.
play on string theory that requires 11 dimensions.
Is that right?
Well,
I'm not,
also
my guess.
AI generated images have been known to have lots of problems with hands, with
Yes.
replicating.
Was that
things.
right?
Yeah.
Okay, this is titled Humankind Arrives on Mars, and he's saying to her out there, I guess, the moon? How could my bags have ended up on the moon? Not back
got
in Newark at the airport. All right, that's funny.
it.
So this is next week's. We'll do this week's next. Uh-oh. Here it is, the one that Bruce commented on, a pi,
So did Gary.
P-I-E, without 3.14, and all those other numbers. It's just a 2.7, which is the E, what is it called? The Euler
Euler's
number.
number.
Naperian base. Naperian base.
That's
Yeah,
another
the
name
period.
for the same
From
thing.
my years as speaking German, I always called it Euler's angle.
That's correct.
Right.
It's German for owl, Jerry.
Anyway, what?
And his first name is not Euler?
Euler.
Euler.
Last name is
Euler.
Euler.
Never heard of Euler, right?
In German, you say EU, oi.
Oi.
Oh, I didn't know that.
As in oy vey.
Yeah. Oy vey.
But he was Swiss, wasn't he?
That's right, Chuck.
Yeah.
Or Deutsch, which is spelled D-E-U, isn't it? Deutschland?
Yeah.
Mhm.
So this
This
is a pie, like you eat with like apple pie. But if
Yeah,
you take
right.
away PI, which is 3.141592, whatever, you take that away, you're only left with E, because that's pi is the number. You're only left with E, and E is Euler's number, and that is 2.71, whatever this
Okay,
is.
does it go on forever like pi?
Yes.
yes.
And is it possible, without going into a long mathematical diatribe, Mr. President, to tell us what the hell 2.71828, et cetera, is? What does that represent?
It's not a simple ratio like the diameter to the circumference of the circle.
Right. So Ron, when you solve a differential equation, okay, that has base E in it, this Euler's number, okay, it's not log, but ln, natural log.
Yeah.
So
Tim, there's more of that for you today, by the way.
Oh boy, I hope so.
I got 2 humdingers for you. I'll bring
Uh-oh.
them.
I remember reading about how when Feynman was assigned to the Manhattan Project,
Yeah.
he went and worked in Los Alamos.
Mm-hmm.
He used to have fun playing around with the security guys. And one of the things he tried doing was they had these safes that they put in the top secret information into, and it was all a bunch of physicists. So he would go around and he would try pi and Euler's number as the combinations of the safes, and he was able to open about half the safes in the place.
Very good.
So that 2 number represents a logarithm?
It's the base of a logarithm,
Right.
a numbering system, just
Natural
like
logarithm.
CAD-based.
Right.
Trigonometry, you have a lot of the functions sine and cosine that can be written as e to the certain power,
Right.
I pi and stuff.
You see stuff like this, Ron, in exponential growth and decay, solve differential equations. It's just a standard, it's a standard.
So the
Constant.
audience should have figured out by now we don't have a simple answer.
Yeah.
Okay. Well, Tim and I are somehow wrapping our brains around it.
Okay.
This one, I think I finally sort of figured out. The Earth's Schwarzschild radius is about a little more than a third of an inch across, which is why safety regulations require desktop globes to be at least 4 inches in diameter. Otherwise, they're a black hole, right?
Yes. The
Yeah.
Earth, if you can take the Earth and squeeze it down to 0.35 inches in radius, then the Earth will become a black hole. Anything in the world, anything you can think of, a textbook, your coffee cup, a tennis ball, anything can be made into a black hole if you squeeze it down to its Schwarzschild radius. Some of
Would
those
that be-
things, like your textbook, that would be probably smaller than a proton to be a black hole.
Yeah.
So that would be the radius of the event horizon, or
Yeah,
the
basically, yes.
event horizon is.
Yeah, just
Okay.
a little bit of history. So Schwarzschild died in the First World War.
Oh, yeah.
He was basically gassed in Belgium. Okay, he did fight for the German side, but he was the very first person to solve Einstein's equations. Okay, and he didn't call it a black hole, but the solution he came up with was something that mysteriously later on would be called a black hole.
Mhm.
He was the first one to solve black holes that don't rotate. A fellow in Australia named Roy Kerr, Kerr, was the first one to solve a rotating black hole, but that wasn't until the 1960s. Okay. Schwarzschild died around 1918 or so, and there's a really good story about him in a book I just read called The Crack in Everything. It's a really interesting book and has a wonderful history of Schwarzschild. Okay. In his relationship to Einstein, he was in the trenches and he would mail solutions to Albert Einstein in Berlin.
Yeah, I was going to say the same thing.
And Einstein didn't know all of this. He didn't go that
He
far.
didn't solve them. No, Einstein was an awfully good mathematician, but he didn't solve his fundamental equations for this exotic thing that we now call a black hole.
We
But,
didn't get into really solving his equation in any kind of detail or usefulness until we came across supercomputers with numerical analysis.
Right,
And
but
close
this is
form
just
is very
analytical
hard to
solution,
solve
Jerry.
that equation.
Yeah, it was an analytical solution,
Yeah. Yeah, early on, this very simple cases were solved analytically.
Mhm.
Well, I can tell you've given a course on this.
I have. I taught a lot.
Yeah, good discussion.
Oh yeah.
All right.
Yeah. Yeah. If you want to do this sometime, Jerry, it'd be fun.
Okay.
All right, this is the Carp DM cartoon showing a spaceman
Yeah,
where
Carpe
on
diem.
Mars. Carpe diem.
He's on Mars waiting for the
Oh,
checking
the
his watch
latest
against
rover
the
to come by.
rover's arrival.
It's pretty good.
Well, I'm amazed that all that silly stuff you sent us that I was prepared for, I guess we can do next week, or did it disappear through AI from your screen?
No, I think we covered all the stuff I had planned for this week on funnies.
You know,
What's
real
Carpe
quick,
Diem? What is Carpe Diem, Tom? What does that stand for?
Seize the day.
Seize the day.
Seize the day.
oh, for
Chuck
crying
always
out
advertises Carpe Noctem.
Yeah.
Seize the night.
loud. I want to save that cartoon for Martin Cakin, since his rover is up there. He had nothing to do with the rover, though, did he? With
Well,
Perseverance.
except that the helicopter was transported up there on the rover.
Yeah, it's
Well,
true.
I don't know what you did with this graphic, but it was a lot sharper than it normally is.
Okay,
Brighter.
good,
Reminds me of the planetarium show.
good. This is from my planetarium software on this machine, the Sky 6 by Software Beast.
Incidentally, is that going to be the subject of your speech on Wednesday at 1?
No, the thing I just gave an arbitrary title to the thing of what's a star, and the bones of the talk is going to be that, how stars, the life cycle of a star, starting with a dust cloud and nebula, going through, depending on how much mass it can grab gravitationally, it produces different size stars. All the properties of the star are determined by its initial mass. And then it can end up as either a planetary nebula, or it can end up as a neutron star or a black hole. And then I will tell people about general relativity and tell them some things that I hope to have a few shockers in there for people. We have a lot of right-wingers in the community, so this
Well,
should be fun.
Tom Whittemore is going to expect a follow-up for the newsletter on that very topic.
Here, I'll give you a write-up.
That'd be
Okay.
pretty good.
Okay, so this one is, I think I called this a preview of the late fall evening sky, but now we can see it rising about midnight. So it's getting ready for the evening, but we can see it now. And the major thing up here is the keystone. And the reason what's that?
Keystones.
The
They look like
keystone of Hercules.
Yeah. See, the shape here looks like it's on its side, but it's the last shape you put into the arch of stone when you're making a stone arch like the Romans used. The Incas or the Egyptians never understood how to make an arch. There are no arches in ancient Egypt. It was the technology that was a step beyond them. And it cracks me up when I read on Facebook about people saying, well, there was communication around the whole primitive world, and there may have been, but it's not indicated by the fact that every culture started with a pyramid. It's just that's the most orderly way to stack rocks. And so everybody came to that first. There's no secret in that. Then some developed an arch. The Egyptians never did. They had what's called corbelled vaults, which as the walls come in, you move the walls together a little bit in a step fashion until you have something that spans.
But
and then
you know, something similar to this that even carries it several steps further is igloos. I swear I don't know how.
Igloos use that same thing.
I know that.
Hole in the top.
They must have several keystones in an igloo.
Well, it's a
They're a
three-dimensional.
dome.
What?
They're a dome, D-O-M.
Yeah.
I know that. I don't understand the keystone concept. By the time you get up there to put it in, everything would have collapsed, wouldn't
No,
it?
you have
Yeah,
it.
that's
held
what-
up by a- you
Yeah,
have it
that's
held
what you
up
call
by
the
a wooden
keystone
bar.
cops, Ron.
I'm sorry, Tom Whittemore?
Oh, I just said that's when you call the keystone cops.
Okay.
Yeah, think
No,
of
the
a
keystone is-
three-dimensional
They build
keystone.
a framework out of wood that they lay the
So they held it up until the last minute, and then it just
hold it
sort
up
of
the
falls
last
in.
minute. The last thing they put in is the keystone, and now they can remove the wood.
Yeah. Chuck, did you want to comment?
I was going to say an arch is like a two-dimensional version of an igloo. If you take it to 3 dimensions and rotate that arch around, now you have a 3-dimensional keystone at the top.
But I'm
And
sure
as-
they don't build a lattice work of wood inside an igloo. How in the world do they keep it to that last piece in the middle?
No, they can get snow to stick together.
Yeah.
Is that what
Not
it is?
that big a structure. But like Bruce was
Okay.
pointing out, in Rome, they built a wooden arch to support the stones until they put the keystone in. Once the keystone is in, then you can take away the wood arch. And the tradition was in Rome, I'm told, that the architect had to stand under the dome while they
Below
removed
it,
the
yeah,
wood.
that's right.
Makes
You know,
sense.
the designer of a submarine has to be on the first dive that it takes.
That'll
Serious.
teach 'em. Yeah.
Okay.
Ron, Ron, that
So
just
anyway, okay, go
goes to show
ahead,
you,
Tom.
Ron.
Tom?
that- Yeah, dome wasn't built in a day.
Yeah.
Okay, when did
When
I lose control of this meeting?
Yeah, exactly.
Anyway, you can see a lot of really interesting stuff up here. We're starting to get into the Milky Way. It's starting to rise here. We were looking out in the evening, it's a little earlier than this in March and April. We were looking out of the north part of our galaxy, and we could see the realms of other galaxies, which we'll discuss if we get to it in time, other galaxies. But
Oh, yeah.
this is the keystone up here.
And actually, the North Galactic Pole is kind of overhead in May, directly overhead.
At our latitude.
Yeah, you
Well,
can
then
see
that-
the Milky Way's going around the horizon.
Now,
Okay.
that's not the North Pole of the Earth.
Right.
That's the North Pole of our galaxy.
Yeah.
Oh, okay.
What is that shape? A rhombus?
I think so.
Yeah, or quadrilateral.
Trapezoid.
Trapezoid, I think, is better.
Oh, trapezoid. Yeah. Okay.
So I think rhombus is more this shape down here.
Yeah,
Mhm.
yeah. It's a squashed square, a squashed rectangle.
A square that's about to fail and collapse. So these are two easy things to find. On this edge of the keystone is M13, a very spectacular globular cluster. And down here, and that makes it an easy find when you're manually pointing your telescope. Down here near Vega, and near the double star there, this one down here, right there, is where M57 is trying to point out. The letter M is labeling the ring nebula down here. Very easy one to find between these two stars, halfway between on a line. But even so, with a low power eyepiece, so you can get it all in, it's really hard to spot M57 because it looks just like a slightly bigger star than all the neighbors. So you have to use higher magnification to be sure you've got it. But it's fun to do. And in this area, we have a very interesting double scar. New Draconis. And by the way, it's Serpens, not Serpius.
Right.
Oh, did I read it wrong?
Yeah. Serpens.
New Draconis. So this is a photograph of the double star. They're equal size stars, equal brightness stars.
So
Both
beautiful
magnitude.
double.
They're separated by 61 seconds of an arc, which is not a challenge for most amateur telescopes. It's one arc minute. And
They're just
they're both
headlights.
at magnitude. What's that?
They're just headlights.
Okay.
Well, Chuck was on a binary Saturday night. Could we not get this one?
We could have, yeah, but this is really wide. This would have been all the way across my field of view.
Yeah.
Really? They're that far apart?
Oh, yeah.
61 minutes seconds is pretty far apart.
You can
The moon-
almost,
the moon
you
is
can almost
30
nail it
minutes
with
in diameter.
binoculars.
Well, could we not see this one because of the moon?
No, we could have seen this one. It wasn't well placed for me to look at it. It would have been in a tree.
Oh, there you go. That's what it is.
The reason
Okay.
we're looking at this star and where it is because it's a star and it's full moon tonight, or tonight. And so you're not going to see a lot of faint fuzzies. So looking at stars is what we do, and away from the moon.
Yeah,
The
near
last time I
the
looked out and was able to see the summer triangle. That was about 2 a.m.
in that same area, Jerry, the Epsilon Larry, the double. That's one that's tough.
Wow.
Yeah, the double up here. You can't see it probably on your screen, but the software is trying to make it one dot intruding on another dot right there. But Vega is a very bright star, a very interesting star. It's a big star, and it's spinning so fast that it actually has an oblate shape to it.
Oh, really?
Same for Altair.
Yeah.
Really? Okay.
Now this one, and it could have started out bigger, but it spun everything off. So this is the limit you see with its spin rate. This shows our sun, which is also an oblate star, very slightly because of its spin, but nowhere near compared to the oblateness of this one.
And I think with Vega, we're looking at it nearly pole on.
Yeah. Yeah, it's just drawn that this thing's spinning faster than the Earth.
Can you see that oval shape in your lenses?
No.
We can't resolve any stars with our equipment.
Okay.
Except the
Just gotta
sun.
trust.
Except what?
Well, is this a
Oh, the
photograph
sun,
or an
yes.
artist's representation?
Yeah.
Oblate just means oval then, right? Or spinning widely. You would think that you'd be able to see it in Jupiter at that big and that fast.
You can. You can see it in Jupiter.
You can?
Yes.
Yeah.
Oh, yeah. That's
Yeah.
easy.
I'm sorry, all the pictures I've ever seen of Jupiter, it's a round ball.
No, you're just not looking at it critically. But if you capture the picture and take a compass and try and draw a circle around an image of Jupiter on your photographic film on your paper, you'll see it's not round.
Yeah.
The best way to learn this is to sit down and draw Jupiter through your telescope, which I did in the 60s. Then you start out by drawing a circle on paper with a compass, and pretty soon you realize the features don't fit in a circle.
Didn't the Earth spend it 10 hours a day in the past?
Yes.
It's slowing down, and so Jupiter probably is.
I heard a number once that it spun at 2 hours before it was hit by Theia.
It was, yeah.
Yeah.
It's
It
been
was
slowing
oblate.
ever since.
Yeah.
Well, I guess it was oblate back then.
How do they figure
It is
that
now.
out?
It's oblate now, but the oblateness is only shows up in the water.
Yeah.
How
We
did
call
they
it
figure that
tides.
it rotated at every 2 hours? That'd be a hard problem to go back.
You can
Gonna
see
take
the effects of the tides on rocks and stuff.
Huh.
Gonna take another show, Tim, just to cover that topic.
Yeah.
That's the thing about doing astronomy shows like this. There's an infinite number of things to pursue and discuss that are all amazing. Okay, this is what we see for the moon tonight, May 12, 11 p.m. It's down in where will be the summer constellations over near the core of our galaxy. The Sagittarius is just out of the field
Kind
of
of down
view.
to the left.
Yeah, down to the left. And we're seeing the Scorpion come up with its two claws here, and its two used to be claws up
Way up
there.
there.
Zubin el Shamali and Zubin el Ganubi, my two favorite star names.
Say them again. I didn't
Try saying those fast 3 times.
Tonight's moon is the flower moon.
Why?
I don't
Because
know why
flowers are
these
blooming.
things come, but they usually come from
Tis-
farming history.
This is the season, you're right. Or the Lompoc moon, depending. They used to grow a lot of flowers up there. It's all green stuff.
Mhm.
Wow, that's pretty much how it looks Saturday night, isn't it? Right there.
This
It was in a different place, but yeah.
this is what it will look like tonight at 11 p.m. Yes. So it's coming up. Well, it's opposite the sun. It rises when the sun sets.
Well, they were managing to see Jupiter in the Palmer Observatory scope.
Yeah, even though it was low.
Mm-hmm.
They even told me they saw the lines, the strata, and I didn't believe them.
No, those are easy to see.
Really?
Usually.
I'll be damned. As
The
far
double
out as
cheeseburger.
Double cheeseburger.
This is the western sky, away from the moon. And again, you can see Mars is up here in Cancer. This is now in the west at about 10 o'clock. So the moon's a little lower in the east this way. Jupiter is just about to set for its trip to the morning sky in a few months. We have bright stars, Castor and Pollux. And we also have two asteroids about midnight, about this time. 9 Metis, which is shown here. And this is made from, it has not been resolved photographically, and it has not been visited by spacecraft. But from the light the change of the amount of light we get from it, they have a program that infers what the shape would have to be. And so they fitted its slight deconvolution of the structure of the light. And this is the shape that they're estimating for the asteroid.
that's just one different views of just one asteroid, one of the two asteroids. This is
Yeah,
Metis.
as it rotates.
Oh, okay. So it's definitely not a dwarf planet.
Depends on the definition of things. This is asteroid 3 Juno, which also has not been imaged. Well, this has been imaged. This is an image picture, but it's a radio telescope. The Atacama Large Millimeter Submillimeter Array. It's the third asteroid ever discovered, but it wasn't discovered by radio telescopes. It was a dot in the sky. Now, the reason that we're jumping to a neutron star
Ooh,
is because, oh, I thought I had another picture in here. Oh, I have it. It's following up. Should have in the wrong order.
one giant leap
This is
from
up,
mankind.
up near where those asteroids are. Let's see if I've got those. These are the asteroids that we just showed. 4 Vesta is above the moon. That's this red dot here. The planetarium software I use shows red dots are asteroids. It has 3 Juno over here, and this is 5 Estrella lower down here. Up here is the globular cluster M5 near the moon at midnight tonight. Now, M5 is an interesting globular cluster.
In that,
It's-
why?
Yes, I'm working on that.
Oh, okay.
It's known to have 105 variable stars. 97 of them are RR Lyra type, also called cluster variables, and they're somewhat similar to Cepheid type variables. The
In
brightest-
fact, that was one of the reasons that some of the initial distances to things calculated were wrong, because they didn't know there were 2 types of these variable stars that had a period luminosity relationship. The
Right.
RR Lyrae types and the Cepheids.
Yes, thank you. This is a close-up of Messier 5, and the brightest star down here is 5 Serpentis below it. So the name Serpens seems to give this crowd trouble pronouncing its various forms. Serpenius, Serpens, and Serpentis. So
Yeah,
this
that's
is
a possessive case, Jerry.
What's
Just-
that?
That's just a possessive case, Serpentis.
Yes.
Yeah.
But this is it's a close, I think it gives us a good aspect on what's going on in the globular clusters. These clusters are very old stars. They have, the cluster contains 2 millisecond pulsars, one of which is a binary. And the binary could help our understanding of what's called neutron degenerate matter. So out of this cluster, they pick out, and I can't do it here, which star is, oh, there's a nice little galaxy back there. The pick out one that is a neutron pulsar. Oh, that's right, pulsar.
It pulses.
Yeah, it pulses. And neutron, it's used to understand neutron degenerate matter, which is a form of matter that is believed to inhabit the core of neutron stars. Let's see if we can get back. Oh, I'm going the wrong way. There. So this is a representation of
Really washed out, really washed out.
Okay.
The basics were there. The names were readable. A neutron star is the remnants of a supernova, right? Of an exploding star.
Yeah, if it's not enough mass left over to make a black hole, you get a neutron star.
Right.
It's
Oh,
not
wow, this is much better.
It's not a white dwarf.
No,
It's not a magnetar.
No.
could be a magnetar.
Yeah.
Could be a magnetar.
So the idea is that when a star forms, and this will be a key talk on Wednesday, but there has to be something. The gravity is very strong in this material, and it's always there. You don't have to have a reaction going on to feel gravity. Gravity is always pulling things in, mutual attraction. There has to be something to resist it, to form a dynamic equilibrium, to have a shape. Otherwise, it just collapses into a singularity, a black hole. This has a resistive force on it called electron degeneracy. It's a property of fermions, and it is what's called Fermi's exclusion principle, that no 2 fermions can occupy the same state. So they have to, if 2 fermions come together, they have to offset their energy levels very slightly. They can't actually get together. And that is the resistant force that holds this as a neutron star, is this Fermi exclusion principle, Pauli exclusion principle for fermions.
And neutrons obey that too, not just electrons.
That's true, but neutrons are fermions and electrons are fermions.
Yeah.
It's observed in electrons too, and we can observe the process in the lab in fermions. That was my thesis topic, was superconductivity, which is a form of neutron, or not neutron, but boson collapse. If they were electrons, you couldn't get them to collapse into the ground state. They can't all occupy the ground state at the same time. So these fermions, neutrons, can't occupy the same space. So they come down in this Fermi Pauli exclusion principle, stops them from getting any closer together. And that's how you get a neutron star. If there was a slightly large amount of mass, then the gravitational attractive force would overcome the Pauli exclusion principle, and it would crush down to a black hole. So this is the last stage you get to. And the neutron proton Fermi liquid is down here, which is where, let's see, these are ions, electrons, inner crust. They don't distinguish it that way, but these are where they're single particles. This is where they're a collective particle. This is where a Fermi gas is up here. This is where things are crushed together farther, and it becomes a Fermi liquid with a few electrons as a Fermi gas. The difference between a gas and a liquid in this sense is that the gas is only interacting with the surrounding matrix or environment. The liquid is that the fermions are now interacting with each other, and they're called quasi-particles or dressed particles. So that's why we have this particle, this drawing here of a neutron star. Oh, there we are.
Okay. Mr. Prez, a fermion would be any particle made of quarks. What would not be a fermion?
A fermion is anything that has half integral spin. Spin 1/2, spin minus up a half, or 3 halves, things like that. So electrons do that, neutrons do that. Bosons are things that have integral spin, and they do not obey Fermi exclusion principle.
So, Jerry, 2 fermions can't walk into a bar?
Yeah. They can't sit on the same stool.
Yeah,
Okay.
that's a very good response, yes.
Well, there's no string theory in there at all, is there?
String theory is about 10 orders of magnitude smaller than this.
Yeah.
Oh, I see. That's your quarks.
Right.
No, that's well beyond quarks. Quarks is down here.
Right.
Here we get quark and gluon plasma.
So Ron, trivia question for Ron.
Okay, hit me.
How many pints in a quark?
Let me check my dipstick and I'll let you know. Oh my God, I'm down a quark. Okay,
well, I'm
Thanks,
going to have
Jim.
to shift back because that method of displaying images says I've run up the last image, and I haven't. So
well, now do they all spin, or can they just sit there and not spin?
they're not really. It's a
Spinning.
property that's like rotation about an axis, but it's not really rotation about an axis.
Right.
Spin is a little bit of a misnomer that way.
Right. It's a degree of freedom, Ron.
Right.
But there are objects that throw out beams on the axis of the spin. Is this one of those two?
That's of the gross object, yes.
Yeah.
The poles, that's a real spin. That's not what we're talking about quantum mechanical spin.
Right.
That's synchrotron radiation.
But can a neutron star throw out a beam?
That's an electron in a magnetic field.
I got you. Here we go.
Okay. So now we're shifting over to our sun.
Squeaky.
It's been unusually active. These are recent solar cycles. Cycle 24 sunspot number prediction from 2016. So here we are with measurements. They count the average number of sunspots to get these curves. This is solar maximum number 22, solar maximum number 23, solar maximum number 24, and this is 2020, we're now in 25, we're somewhere up here for solar cycle number 25. And there's a lot of flare activity.
Mm-hmm.
And this is a diagram of how the topic here is magnetohydrodynamics. It's the flow of particles of fluids in a magnetic fluids in a magnetic field that generate the magnetic field that they flow in. So the math gives me a headache, but computers help. But this is the photosphere of the sun, and this is a bulge. This is what happens in a flare. The magnetic field, which can't start or stop anywhere here, it's always a closed loop. It has been squeezed out of the normal flow of these magnetic flux tubes, and it's forced through the photosphere. So this would be a sunspot, and this would be a sunspot. And up above this, if it's like this, it's a prominence. If it's energetic enough and it goes way up, then it becomes a flare. And so these are sunspot regions where you can see the magnetic field lines going out, and here you can see them looping over and coming back. And here's one this was a video, and I captured right as the flare went out. This was in May of last year, and we got a CME out of it, but it missed the Earth, because if it were coming toward us, it would be right in the center of the picture. But this is a flare coming out. It's something that was thrown up so energetically that it actually broke the magnetic field lines, and then they reconnected independent of the sun. So now it's its own ball of plasma, like ball lightning, headed out into space.
Really?
So this has been a very active solar period. This shows composite view of the sun for our current solar cycle, with all the prominences and flares that we've been enduring. Last May, I think it was, we had a CME that came by the Earth, and it actually tripped the surge protector on my computer, but it didn't damage the computer because I had the computer on when we were.
That almost looks three-dimensional, that image.
It does. Yeah, but it's two-dimensional, I guarantee it.
Huh. Wow.
But that solar flare, when it gets into space, becomes a heavied up solar wind. If it hit us, would it destroy us?
It'll go ahead, Chuck. You're muted.
You're muted, Chuck.
Muted.
Can't hear you.
That's what causes auroras. You get the normal proton wind coming out of the sun, you can get auroras, but when you get them really far south and really strong, that's when something like a coronal mass ejection has hit.
Okay,
I have an AD switch that's on my computer on the Cat5 port that the B channel of it connects to nothing. So if I'm not on the internet or my computer's off, I push the number 2 button and my computer is not connected. So, a glitch from CME should not affect me. Shouldn't break anything, let's put it that way.
Yeah. And that's a good choice of words. Should not. Yes, because it doesn't.
Can I read something into those 2 bright spots? You just changed it on me.
This one here?
No, that last shot of the sun. Yeah, seems to me there's 2 levels just north and south of its equator of whiteness. A bright, what is that? Is that where the sunspots happen?
Yes.
Mm-hmm.
Really? They don't happen on the top or?
They do, but they gradually progress toward the equator.
Right.
So this isn't the entire cycle.
No. This was last year of the cycle. Last year, 24, I believe.
So this would be a time exposure.
It's what?
Basically.
It's a
Composite.
Yeah,
composite, right? Yeah. Collage.
This is made. I guess it wasn't our current solar cycle. This is 2013 and 2014.
Okay.
But it's a composite of that period. Now these you get solar cycles.
23 and 24.
What?
23 and 24, not 213.
2013 and 2014.
Huh.
So the last cycle.
Yeah. That would be.
Mr. Krez, you just sent us a website called Scientific Sensuality or Sensibility. What the heck it was? Sensitivity. The last week, it's been really blasting. So that's what we're looking at the last week, I guess, right?
No, this is 2013 and 2014.
Yeah.
Okay, but there was a website that he sent us showing something action, heavy activity this past week. It had the
Yeah.
word sensuality
Yeah.
and scientific in the website name, scientific
Yeah, I was
base.
just showing you what went on the last few days there, but it's not in this presentation.
Oh, I see. Okay. 'Cause I remember looking at it.
We have enough trouble explaining what we're showing.
Well, it's a 22-year cycle, 11 and 11. Where are we on the upper limit or the lower limit right now?
Right now, we're at the
Nader.
right
No,
now.
we're near the peak of activity.
So
Yeah,
that's the upper, that's the most.
this is 24 here.
Yeah.
We're out here, and we're expecting a lot of activity this time.
And it might even be a double peak.
Yeah,
Huh.
You
And
can
we've
kind
been
of see a
keep-
double peak in that central one, the cycle 23.
hmm right there.
Well, at the solar party at the museum on the big scope, you could see there's a very nice, very large couple of sunspots.
Yeah.
Do any of you know how long we've been keeping track of this?
Since Galileo.
Well, they've been
Really?
recording it, I know, since I just read a book on the history of Lick Observatory, and they've been doing it since that period. And then they started building Mount Wilson. That's the 1880s. They started building Mount Wilson Observatory. It went online in 2017, and they have several solar towers that were the first things to go up there. So they've been counting sunspot cycles since 2017. So just a little over 100 years.
But people have been, noting sunspots and
Yes.
how they moved and how they looked since Galileo's time.
Right. But they were quiet about it at first.
Yeah.
They had filters back then. They could look at the sun.
Well, they would project
With
onto a piece of paper or something white.
Yeah.
Well, does
That's
it?
what the big solar scopes on Mount Wilson always projected their image, which came out to be about 2 or 3 feet in diameter, on a big easel in paper, and then they'd reach out there and they'd draw in the sunspot that they saw on the paper.
But is this the same thing as the sun possibly essentially getting a little brighter and a little less bright over the 11 years?
Yeah. It's actually when you get a lot of sunspots, you get these plages. So you'd think the sunspots would darken the sun down, but the plages or plages means beach in French are brighter than the sunspot. And so the sun actually is a tiny, tiny bit brighter when you have a peak of a sunspot cycle.
Oh,
No,
But it's a very small effect.
man.
Yeah, it's not going to account for global warming.
Yeah.
Okay, got it.
that was the Maunder minimum, right?
Maunder minimum was back in the 1600s.
Yeah, that was where they tried to tie it to the ice ages.
Yeah.
Didn't work.
Well, they
it
did
didn't
have a
work.
little mini ice age at that time, but the cause and effect isn't clear.
The ice ages appear to be related to very small fluctuations in the Earth's orbit and eccentricity around the sun.
Really? Is that
Yeah,
much
I
of a
think we discussed
disparity?
that. If not, then I'll find that article again. Okay, moving on
Yeah.
to galaxies.
Galaxies are us,
Yeah.
all sizes, including dwarfs.
Now we've seen this before. This is the Hubble Galaxy Classification. I think it was first put together by Edwin Hubble or Fritz Zwicky. They had an opinion on which way it went. It went from here, and there was arrows here to go these ways. But I think the belief now is that the arrow goes the other way, because these things, the different elliptical galaxies, have much higher masses than these things. But then there are galaxies that are very small too. So I don't know yet. But anyway, this is a good view of part of the Virgo cluster. And it shows Markarian's chain going up here. And you can see a sampling of different types of galaxies. There are, and that's what we're going to really discuss really quickly, is the different types. As you saw earlier, this is an edge-on spiral. There are elliptical galaxies which have no spiral structure. Now I can't find any, but there are actually most of them. Any comments, anyone?
Well, I was going to say, they used to think that that fork diagram, the Hubble thing, was an individual galaxy sort of evolving.
Yeah.
But nowadays, it's more the thought that when galaxies interact, then you see the progression from spiral to elliptical. You need to have another galaxy interacting to get some of that change.
And Chuck touched on a problem with astronomy is that most of these things happen over not even geological or not lifespans, but geological ages. And so we can't see things evolve. We can just see things at different stages of evolution. But we don't know really what happened to get to that stage. So we're putting things together and guessing at it and modeling it. Someone else comment?
Is the Virgo cluster you just showed a part of our local group?
Yes.
No, but the local group is part of the Virgo supercluster.
Yeah. Right. Good. Yeah.
Okay, so these are all the galaxies closest to us, around us.
These are some of the galaxies close to us.
Got it. Okay.
These are the ones you would have seen straight up in the evenings in March.
In the middle, are
they're more like straight up now. In March, they would have been on the horizon.
Okay. So galaxies orbit each other just like binary stars, those two in the middle?
They gravitationally interact. There's a large chain of galaxies that's very long, and it has galaxies that clearly interact with each other, but they are not orbiting each other, but they are interacting. It's one of the very large structures they're trying to identify now and decide if they're all really acting together.
Well, isn't there a big central point called the Great Attractor?
No, that's not a central point.
That's a very, very, very large supercluster of galaxies, we think.
Yeah. Or it's at least a very large concentration of dark matter. Because we get the gravitational field, the strong gravitational field pulling a lot of galaxies, including us, toward this region of space, but we really don't know what's there. Speculation ranges from all sorts of interesting stuff down to that's a gravitational field leaking into our universe from a parallel universe that has a large galactic cluster in it.
Whoa.
Time will tell.
Well, are we looking at a particular galaxy right now, or
this is the Milky Way, but it's really blown out.
No.
That's how it looks. We're a bard.
Well, it's how we think it looks, you know. We're inside it, so.
Well, that tilted galaxy that's a little off on the edge, that wasn't us, but that's, you know, the one I'm talking about, that's
the potato chip shape.
Yeah, right.
Yeah, we seem to have that, but that wouldn't show in a 2D diagram like this, unless you're looking at the edge.
Okay.
This is a drawing, not a photograph, of our galaxy. Here it is from the side, showing the central bulge. And here it is laid out in 2 dimensions. Right here is our sun. That's where we are. We're a little over halfway from the center to the edge. This is about 100,000 light years. Excuse me, 50,000 light years, about 100,000 across, and we're about 30,000 light years out from the center.
And that's kind of depends on where you define the edge too, because you'll see numbers 100,000 across to 200,000 across.
Yeah, I've seen numbers even up to 1 million if you count really outlying stars.
Yeah.
But it's really where the dominance of our gravitational field ends.
And we're located in a spur, not an arm.
We're located right there.
There on the Orion spur.
The Cygnus.
You suppose if we were located in an arm, it'd be a brighter night sky, more stars?
There's lots of places we could be where it would be brighter or dimmer.
God, amazing.
It's interesting now they have the direction of the Andromeda galaxy over there at 8 o'clock.
Yeah. And the Great Attractor in the upper right.
Oh,
I wonder what life is like, or the night sky is like in the bar.
Yeah. Well,
so the Orion Nebula is right there, very close to us. The Pleiades are even closer.
Wow.
Okay, this is our galaxy, a composite of our galaxy, looking edge on.
So this is an actual photograph that somebody spent a lot of time putting together.
Yeah, it's a mosaic. There's the Large and Small Magellanic Cloud, which are irregular galaxies. And this is ours, which is a barred spiral. It's how it looks from our place in the galaxy.
Okay, can it be a fair statement that the supermassive black holes in the middle are slowly eating up all galaxies?
No.
No, they're going to live on, just don't get close.
Yeah.
That eating up is sort of a myth. Black holes, things do fall into it, but not in our lifetime. If you were to look at a rocket ship going into the black hole, initially you'd see it speed up as it got to stronger gravity, but as time dilation takes over, you'd see it slow down and stop. So at the surface of a black hole, you would never actually see anything enter the black hole in the age of our universe. The activity that we associate with a black hole is that spinning disk around it of all the people trying to crowd to the axis at one time, and the interactions. That's what throws the beam out of each end, and it's what causes the emissions, the brightness. So the actual entry into the black hole, you will not witness.
And they wouldn't see themselves being spaghettified?
No, they wouldn't. They would, what they would feel is nothing. It's not the black hole event horizon is not a real thing. It's not a real border. There's nothing to bounce off of. What they would notice if they're looking out is the whole universe around them is speeding up. And before they ever spaghettified die, they would see the universe trillions of years from now die.
Really?
Yeah. It's time stops at the edge of a black hole. Time is zero. And at the center point, the discrete singularity at the inner, according to Brian Cox, is better thought of as a point in time than it is a point in space, because time and space change roles inside a black hole.
But if you don't mind me returning to the beginning of this hour, Mr. President, your Schwarzschild radius is the not the singularity. The singularity is the point, right? But your event horizon, that's
Right.
not the edge of all the stuff that's in there, right?
It is it is the edge of everything you can see.
Yeah.
You can't
It's where
see
light
anything
can't escape
inside.
anymore, but you don't know what the size of the thing inside is.
Right. And the singularity inside is a hypothetical singularity. No one has ever observed it or measured it. It's an
And the Big
extrapolation of general relativity.
And even though it's hard to imagine everything in the universe squeezed into a single point, that's what the Big Bang came from, supposedly.
Yeah. But it was empty then.
One interesting view of the Big Bang is that in another universe, there was a black hole. And the black hole formed and all the matter rushed in. And in all universes, singularities are not allowed. They're not defined. So the material rushes in and it bounces off itself and produces a Big Bang inside that black hole. And the physical constants reset themselves so that, in a sense, like the Harry Potter world or the TARDIS world in Doctor Who, the inside is much bigger than the outside. It has its own scale inside. So it's entirely possible that that's the universe we're in, is a black hole. That's very hypothetical. No one has worked out the math to claim that's it. These are
I didn't hear you mention white hole once.
Well, Einstein puts for every black hole, there's a white hole somewhere.
And that's not what you were describing. Okay.
Yeah.
But that requires that Einstein-Rosen bridge, which collapses if anything goes through it. So
I wonder how the fermions.
Einstein-Rosen bridge is believed to be the string of string theory. And that's what connects it, basic particles. And that's the Nobel Prize in 2022 was awarded for proving Bell's theorem that things are not locally real on their own. Things in our universe are only real in relationship to other things. So for everything we see, there's got to be something else that's bound to it with a string.
Yeah, Ron.
Yes.
Yeah, I was just going to say they were going to build an Einstein-Rosen bridge in the Bay Area, but it collapsed.
Well, on that note, I got to tell you, it's a big reason people love this science. It's
Okay.
just
We'll pick
conjecture.
up this galaxy stuff because I'm only starting into it next time.
You suppose we'll get to this past week's cartoons next week? Because I was all
I'm
set.
going to look for what you consider past week's cartoons because I think I captured them all.
Well, you had the biblical version of the Big Bang. God's trying to check out the instructions on the airbag.
We showed that the week before.
No, I don't think we did.
That is a repeat, but it was a long time ago.
Well, gentlemen, as usual, you all strike me. Thank you for watching our 219th Astro Hour. We'll be doing it again next week, exploring the cosmos. In the meantime, Chuck, would you like to give the official farewell, our favorite adios?
Hasta nebula.
Okay.